So we are going to control hardware today, and we are not going to use any sophisticated tools or programs for such. Instead, we are going to be using the tools that we regularly use in Linux for normal file reading and writing purposes. Well, for starters, I have the system monitors open up here. It's showing all the different stats to my system. And these are all the different CPUs, 0, 1, 2, 3, it goes till 15. But if you see, this is from 7 till through 15, the CPU shows offline. There is no temperature, nothing. It is being, although the CPU is doing the basic, for example, if you see the up till CPU 6, the system is using the CPUs, but from 7, you can see nothing is being used. It's like the CPUs doesn't even exist, right? This is the first thing that we are going to control. And frankly, the only reason I'm controlling this is because Linux allows us to control these things with just files, writing files. And I thought this would be a cool start to our video, no? Watching us make our CPUs offline. Well, what we did was we sys class, not sys class, there is for devices system CPU, and it has all the different CPUs available. The core, my system has 15 threads, 16 threads, the 8 core machine with 16 threads. But now if we see, let's say we go to CPU 15, and we say see what is the online status of this, and we see it is 0. But similarly, if we go to CPU 1 and online, we see it is 1. Now say how to make these CPUs, how to bring these other threads or cores online. To do that, what we need to do is we need to say, for example, 7 is currently offline and is also visible from here. CPU, it's actually 8.1. We are counting from 0. So it says the 8.1 is actually offline with the number 7, CPU 7. But if we write 1 to this file, actually what, yes, let's say I show you how to do it in a normal text editor. I of course have to start the editor with administrator privilege, because you don't, normal user cannot just do their way with making CPUs offline. So that's why I'm using sudo, and you will see this says 0 at the end, at the start. And if we just type it 1 here and we save it, now if we close this file and see this again, you will see system 7 has actually come online. Sorry, the core 7 has actually come online. What we did was we just wrote to this file and the hardware behaved accordingly. We basically control the hardware through this file. Now, obviously, we don't do Vim, because opening Vim, we can use any editor to control these files one by one. But what we can do is we can say 1 and sudo t. So t is a simple program which takes in whatever is given. This is the pipe operator, of course. It takes in whatever is given from the standard input, and it writes it to the file that is provided. So here 1 is read, echo 1 is basically doing echo 1, it's basically writing 1, and we can say echo 1 let's show you how it works. Echo 1 t hello.txt. Now if you see, there is a file called hello.txt and it says 1. Similarly, if we do, let's say, hello, and with double hello world, and we say t, and t, by the way, also writes both at both places. It writes to the file name we provide and also to the standard output. So it's basically, we can see that what it has written, and that data also gets written to the file. So now if we say hello.txt, it says hello world. As expected, we are doing similar thing with this one. We need to write 1 to this file, and write 1 to the terminal, and take that one and write it to CPU 7. And use sudo, of course, because this file with Linux won't allow us to edit this file with normal user privileges. But since 7 is already online, let's try 8. And now if we see, 8 is also online. So now the only CPU cores offline are from 9 through 15. So we can actually go ahead and do something like, okay, CPU 9, then CPU 10. But Bash allows us a cool trick. When we say, we open up a this is curly braces, and then say 9 dot 15. So what it will basically do is, it will run this command from individually, and every time it will increment this number. First it will run for 9, then 10, 11, 12, 13, 14, 15, and for every line, every item that it generates, it will run the command. So we are basically writing 1 to the CPU 9 through 15's online file. And if we do this, it's successfully done. And if we do a stop, and you can see all the CPUs come back now. Oh, since there is not much load in my system, so that's why these are not being actually used. But you can see some of them getting used, and also these now doesn't show offline. Now, interestingly, what about other things that we can control, right? Let's say sys plus. If you have a, I'm now on my desktop system. So, but if you're running this on a laptop, you would see basically a directory here. Inside backlight, there would be a directory, and let's say something like, if you have an Intel GPU, then it will be something like Intel backlight, and there would be a file called brightness. Of course, I don't have this file because I am using an external monitor, but sometimes you will have it if you are on a laptop. And of course, this name might be different for you. Sometimes it comes up as is something like ACPI video or something, whatever it is. That's the name of the display as seen by kernel. Name of the display panel, display brightness hardware, actually, not the display. Let's say it sees the display brightness panel as Intel backlight, and there's a brightness. If you do cat, you would see a number, and similarly max brightness, you would also see a number. Now the cool thing is, you can actually control brightness with this. So if you see, let's say, while doing cat, you see something like 7,000, and for the max brightness thing, you see something like 19,000. So then what you can do is, you can say, okay, echo 15,000 and sudo t, and when you run this, it will basically write the value 15,000 to this file, which will cause your display brightness to go into this value, which may be, and you would basically see the difference as your display brightens up, or if you're already above 15,000, you will be basically see the brightness coming down. That's one thing you can actually test. And but let me show you something different. Sys plus LEDs. Now LEDs show you all the LEDs that are connected, that the kernel is basically controlling. So not all LEDs, some LEDs are not controlled by the kernel, but whatever LEDs are controlled by the kernel, you would see this. For example, input 28, caps lock, brightness, you see it is 0. Now if I add and switched on the caps lock and I say it's brightness 1. That's good, but there is other field called trigger. Now if you see trigger, it shows you a list actually. Every space in between actually corresponds to a individual item. So non-default USB gadget, this is and this is the selected one, KBD, caps lock, which means this caps lock LED is the trigger for this LED. So like when this caps lock LED is going to turn on or turn off is decided by this caps lock. But interestingly, we can actually change this. For example, my Wi-Fi card has the name PHY0. Now, if you don't know what card name you have, you can basically say sys class net and you will find this. Yellow would be common. This is loopback, and most probably you would see something like WL, whatever the number is, something, or you might see WLN0 as well. And when whichever is generally Ethernet ports actually starts with E, and WLAN ports actually start with WL. You might see something like WLP4S0 or something, whatever the name is, WLAN0. And then if you say name, I don't know what's the name, then device name, I guess. No, not device. Device ID. How to find out the actual device. Okay, this is weird. How to find the name assigned type. Give me a minute, guys. I have to find out. Def ID, is it name? No, it's the ID in the port. We don't need this. Then we say PH521. This is name. This is 50. This is how you can find this also. But I was looking for a more easier to see or understand something. Don't worry. So basically, you can enp NP5L0. What is how do you find the name of this device? Right, this one. Actually, what you can do is you can also say RF kill also. RF kill, it would also only show you the radio frequency cards. One would be, for example, in my case, I have Bluetooth and Wi-Fi, so there are two. So RF kill 0, if we say name, it's HCI 0. And if we see our type, it says Bluetooth. Similarly, you say RF kill 1, it says WLAN, and you see the name, it says 50. That's how you get the name of your actual name that is assigned by the kernel to your Wi-Fi card. But when you get that name, and we can actually control the LEDs, caps lock, trigger. Now you can see it. RF kill 0, HCI powered. HCI 0 obviously stands for the Bluetooth in my system, audio mute as well. So let's do something interesting. The 50RX. RX stands for receive. Yeah, I know RX. I don't know. Maybe there is a proper word for this, the X. But here is how I understand it. This is the receive part, and this is the transfer, which is the going out part. This is transmit, and this is receive. So if you say, instead of, we say phy0rx and we do sudo t, we change the trigger basically. Now you would see the trigger shows phy0rx as the selected one. And if you pay attention to your caps lock light or LED, you see that it is starting to blink in some random pattern. This pattern is not actually random. It is turning on whenever there is activity, receiving activity on your Wi-Fi. So if I say something like, ping for google.com, now when it receives this data, you would see the ping be going on. And if you do something like watch a video or something which on YouTube, which causes more data to be transmitted, received, then you see the light to blink at much faster rate. Of course, if you are on a if you're running this on a laptop, you would see more interesting things. For example, battery, there'd be like BAT0 power or some BAT0 charge full, which basically you can trigger those configs into the LEDs as well, so that when you can say basically whenever the battery is charging or battery is full, uh, light up this caps lock LED. And of course, now that we are done, we are basically KBD caps lock. We basically reset it to this one, the caps lock light, because uh, now if we do caps lock again, it says properly. So that's some things that you can do. And of course, let's show you the one cool thing actually, which is sys devices, uh, uh, devices system CPU and CPU. We don't go to individual. We can go to individual CPU 0, let's say, and there is a folder called directory called CPU frequency, and here you would see what is the current CPU, the frequency with which it is running. But we are not interested in this now today. We are interested in this file, the energy performance preference. This actually controls what is the current performance mode of the CPU that is currently running. So you might have seen power profiles like balance performance and the power saving mode, balance performance, balance power or something. So this is where the kernel exposes that interface. So if you see, I am currently at my system is currently running at balance performance. I have not changed this. This is the default setting for AMD. And of course, there is energy performance available preferences. And you would see these are the possible options we have. We are currently at balance performance. Performance is obviously the fully triggered tune for performance. Then this is for more power saving. Now what we can do is we can say, okay, energy performance. Please note the name. This is one of the available preferences, which shows you what are the possible values it may have. And this is the actual file, energy performance preference. This is available preferences. Now if we say, okay, go performance and sudo t to this file, we can basically change the performance of a single CPU. Of course, for example, CPU 0, if we do this performance, invalid argument. Okay, I mistakenly made a typo. It's performance. And now if we read this thing, for CPU 0, it says performance. For CPU 1, it says balance performance. Now, obviously, what we did for one CPU, we can also do it for all the CPUs. Say 0, true, 15, and we want all of them to be running in performance mode. So this is there. And now, if we do cat on this, you can see all of them are running in performance mode. Now, bear in mind, if you are using a desktop environment, I'm not using a desktop environment. The desktop environment will show you a GUI option of seeing what is the current performance mode, and you can change it from GUI also. Internally, it is doing the same thing. But the thing is, if you change it here directly using something like echo, you might see the GUI might not reflect what you have already there. But if you do it via GUI, it would reflect it in here. The reason this happens is your CPUs are controlled by something called as power daemon or power profiles daemon, and which actually basically GUI for profile selection. So when you select something in the GUI, it says, okay, it talks to the daemon, and daemon is basically in background services. So the background power service actually something called uPower or power. I don't remember power service name, but uPower is one of them, I guess. And then it talks to the CPU and changes the this profile. But when we do this echo performance directly, we change it directly at the CPU level. Actually, you can say there is kernel is actually present. We change it directly at the kernel level by writing to this file, and kernel makes sure CPU is updated accordingly, the hardware is changed accordingly, configured accordingly. But power profiles daemon doesn't keep checking what is the current set. It just remembers what it last set. So that's why when you change it from the GUI, it might not reflect in the when you change from the GUI, it will reflect in the kernel using this file. But if you change it directly from the kernel level, you might not see it in the GUI section. So this is something to keep in mind. Now, the thing is, you might remember this slide, procmem info. If you see it basically gives you an information about the memory. Of course, you cannot write to this file. I'm just showing you something for a different reason. This file is purely read-only file, and if you can basically see ls-l, if you see, it says it only has the read permission. The write for every group and the execute permission are missing from this file. This file is meant to be read only. So read only. But if you see, the size of this file is 0. For example, if we see it here, you see hello.txt is 12 bytes. Hello.txt, it has 11 characters, and there is a termination character at the end. So that's why it's 12 bytes. If we add something like, get, let's say echo something like echo hello there, how are you, and we write it to hello.txt. Now this file contains more characters, and if we do ls-l, we would see the size gets bigger. But the interesting thing is, if you do lsl proc mem info, you see the file is 0 bytes in size. Now this is actually a very beautiful proof of the fact that these are not actually files on the disk. These are just the kernel makes them look like a file, but they are not actually files on the disk. You can do all the operations that is available on the file. For example, this file is read only, so you can only read, but some files are write only, allows write. For example, what we did was this one. if we do something like ls-l, you'd see all these files have weird, just give me a minute. Let's say we go to 0 specifically, and energy performance preference, and the size is 4096. So this file has a particular size. This is interesting actually. All of this has is for your frequency, but this is interesting. Plus net WLAN 0 and statistics is a directory, but it says 0. I don't know why some files have 4096 is 4096 comes up when it's a directory specifically. So if you see, for example, here ls-l, all the directories have 4096 because directories are internally stored as files. So that's why it has 4096 bytes. But I don't know why this is showing 4096 bytes, although it's, for example, upper state is actually up, and if we do FNL, it is 4096. Well, I guess this is not a direct proof as to the fact that this file is not present on disk. But what we can see is, maybe another way we can basically see is df-h. It shows you all the different file systems that are mounted in different places, and you can see my third partition is actually how much percentage is being used. And similarly, if we do df %ha, it will show you all the different. So proc contains /proc has a proc file system. It's a different file system. It's not like something like this one. It's a proc file system, sys file system. These are virtual file systems which the kernel manages. And you see all of these has size 0. Maybe this is a good proof as to the fact that these are not on disk. So yes, the files in sys or proc, anything that's contained in sys, anything that's contained on proc are not actually present in disk. They are just the interface which the kernel provides. Now, for example, get proc sys kernel, and you see arc, you would see what is the current architecture of your kernel, of your system, CPU, or something like OS release. You would see what is the version of Linux actually running. You can also see the version here also, which gives you a full, bigger, more detailed version in proc version, but OS release actually shows you what's the kernel release name, release version. And similarly, OS type, which, sorry, OS type, you would see it's a Linux based OS. So that's why the kernel says Linux. Now there is interesting a field called host name, which says depth station. Now you might have noticed this is, if you remember, this is what is the name of my system as I have given through Linux. So I have given the name dev station to this machine, and this is present in the proc/sys/kernel/hostname. Now if we go ls, type in ls-l, we see the root user. This is for the owner or the owner user. Then this is for the group, and this is for all others. We'll not go into this, but the fact that it contains w here, which means this file can be written to. Now if we say echo, let's say ras pc, and we say sudo t. Sudo is required because these files are not editable by normal users. It needs sudo admin root access. Now if we write ras pc to this file, course, it asks for password, and it doesn't seem like it changed anything. But now if I close this terminal and reopen it again, close this terminal, reopen it again, now you can see this is the host name actually changed. It was earlier dev session, now it is PC. Now this is not this is, you can again change it back to uh, something like my PC, and it's changed again. So with this file actually contains your host name, and by writing to this file you require root access, but by writing to this file you can actually control the host name. But bear in mind, these files, that is we just saw, these files are only in the memory. The kernel is maintaining a state of the system, and it is exposing that some of that state through this virtual file system. And we can modify some of the state by writing to these files. But the thing is, whenever we restart the kernel goes back to what is configured. So the hostname, by writing to this file, we are not changing anything. In fact, for example, whenever we wrote this one, so we said we want the Capslock LED to turn on and off based on receive activity on my wireless LAN card or Wi-Fi card. We did not change any configuration. I mean, we did not change any persistent configuration. We did not change anything that is going to remain after restart. We just modified the real current state of the system, and when the system is rebooted, the system would go back to what is the default configuration setup on this system. And for example, this is the current host name of the system, and this file etc, don't get confused by the name. etc generally seems like etc, it contains random miscellaneous stuff, but it is used for configurations. So etc hostname is a file which contains devstation, and this file is used by kernel when it loads up, when it starts up and configures the system. So it reads this file and maintains the state based on these files. So if we update this file using echo something like ab something like this one, and we do sudo t, we basically change the host name, but it is not going to last a restart unless we modify this file name, which is in etc. If we modify it in here, it will persist across. It might not be visible immediately because kernel will not read this file unless until the system is restarted. So it only reads this file once. So if you want to change the host name or the system name permanently, you change this file. And if you want to change it temporarily, you write to this file. Now we will go into why Linux uses this type of files to configure. No? Why it uses normal files at all? I mean, in Windows or any other Windows-like systems, basically Windows, it doesn't use a human readable file. You need specialized tool to change the system host name, or specific, or maybe it allows system host name through file, but it is not kept in a simple text file. We'll go into why this is the case with Unix-like system, the Unix philosophy. But for now, we just saw that this can be changed, and I will end this video with an interesting file, which is power state. Yeah, this is the file sys power and state. Now if we see freeze mem, and this it says 3 words. Now the interesting thing is, if we, let's see whether it allows writing to, and we see yes, this file allows to be written to. And what we can do is we can say freeze and sudo t and run this program. Well, we cannot run this. I mean, we can run this program. I cannot run this program right now, because if I do this, this video recording, this recording will stop. If we guessed correct, if you have guessed already, this basically maintains the state of the system. So if I say freeze, it basically suspends the system into RAM. Similarly, if we do mem, it basically goes into full sleep but keeps everything on RAM, so that you can wake it up using enter or the power switch. And if you do disk, it basically saves the current state into disk and turns off the system. This is complete turn off, but the state is stored in the disk first, which basically means hibernation if you speak it in normal terms. If you do this, this is hibernation. If you do mem, this is like a full deep sleep, but in RAM, nothing, the system is not turned off, but the light will go up, obviously. Similarly, freeze is like, freeze is also a even lighter version than mem. So with that, we saw, I'm not going to run this, but you can feel free to run these commands. These will not impact your system in any way. You can basically test this command, and if you can basically set your system to sleep or hibernation using this, by writing to this file directly, sys/sys/power/state. Now that we think of it, if we say x, can we draw? This is what we were using earlier. Now, if you remember this diagram, we say Linux is not a kernel, it's an OS. It's basically saying OS, the distribution contains many other fields like interface, shell programs, ls, cd, and what we are using currently, ls, t, sudo. These programs are not part of Linux. These are part of the OS, or the, for example, to be precise, it is the shell programs. Then there are desktop environment, then there are applications like Firefox and everything. Everyone, but Linux kernel is the only one. Let me just, okay, maybe I should not have flashbang you. Sorry about this. Maybe it's just them. Okay. Sorry about I keeping it in light mode. Yes, so Linux actually is the only one, or the kernel is the only one which is communicating with the hardware, but it also allows programs to communicate with the hardware. But to do that, you will have to ask it via the kernel. You cannot access the hardware directly. If you basically cannot do this, you cannot do this. This is not allowed. But you have to do it via this, via the kernel. And the ways that the kernel allows you to do this are called interfaces. Interfaces. And there are multiple interfaces, and we just saw one of them, right? We just saw one interface, which is the virtual file system. There are many more interfaces, for example, but those are more related for the programming environment. And interfaces like syscalls or ioctls or Unix pockets. These interfaces are mostly syscalls and IOCTLs, but these interfaces are also a way for processes to communicate with the kernel. And virtual file system is also one interface. We just saw it. We communicated with the kernel and managed some parts of the hardware, control some parts of the hardware. And in effectively, what we did was a different way of speaking with the kernel, whereas programming is one way of speaking with the kernel. And we also did something a similar way, but we used a simpler interface. You can say it's the simplest of the interface to actually speak with the kernel to control the hardware through Linux. Because as we know, Linux is the kernel. It manages the hardware for us. It manages the processes for us, and it allows processes to speak with the kernel to access hardware. So if your program wants to access the hardware, it has to speak with Linux through one of the available interfaces, out of which virtual file system is one. And we use that virtual file system for something and control the hardware. With this, you can basically, this is these files that are present here are not just normal files. These actually are an interface to the kernel itself. These and the proc. Proc. This is also an interface. Proc is an interface to the processes part of the kernel. So, and sys contains the system view of the kernel. Not everything, but mostly it exposes most of the hardware state through this sys file system, a virtual file system. Let's wait. In the next video, we will see how Linux stores configurations in simple text files. Why does it do that, and what are the advantages of using files to store configurations?